Um, this is joint work with Andreas, Abel, and Nils Danielsson. We are from Chalmers and the University of Gothenburg. In this paper, we've been looking at type theories along the lines of, for instance, Conor McBride, Bob Atke, and many other people who are combined dependent type theory with modalities or graded modalities. In particular, we've been interested in Erasure. So for instance, this is the type of one version of a, say, fed function that takes some vector or array of a given length and a proof that the length is non-zero. And we've marked with this 0 on the arrow that this proof is erased. When we actually want to use this function, we of course need to supply some proof. And when this code then gets compiled, we'll typically expect that code will be generated also for the proof, even though we would also expect that the proof would never actually be run. Meaning that if the proof is very long, we'll generate lots of code that don't serve any purpose, leading to the executable being unnecessarily large, for instance. But since the proof was erased, the compiler could use this information to actually avoid generating any code. In order to be able to do this, we allow the eliminator of the empty type, which we use in the actual implementation of the 0 case of the head function, to take an erased argument, meaning that we can use this erased proof or other erased information when we want to discard impossible branches such as this. Crucially, being able to do this safely relies on the theory we're working in being consistent. If it's not consistent, eliminating this branch could eliminate something that isn't actually impossible, which could introduce bad behaviors in the programs like crashes or scary, unsafe coercion functions. In addition to allowing this possibly long proof to be erased, we'll also allow postulates to be used in the proof, meaning that one can add things like univalence or function extensionality or anything else that you might find useful to use in your development. Typically, adding postulates like this would break canonicity, since the postulates don't actually evaluate when we run them. But we've shown that as long as these postulates are only used in erased positions like this erased proof, we can actually still get canonicity for natural numbers. Again, this all relies on consistency, so any postulates that we want to add need to be consistent with each other and with the base theory. This paper has been fully formalized in IGLab. We've been building our work on an earlier formalization on dependent type theory, originally by Andreas, Abel, Joachim Öhman, and Andreas Vessosi, who proved the decidability of equality checking for a dependently typed language, and at the same time proved various other properties of the language that we were able to make use of. In particular, importantly for what we've been doing, they prove that the language is consistent. In our paper, we've been extending the formalization with modalities, which can track, for instance, erasure, but could also be used for other modalities as well. More concretely, the formalization is now parameterized over a sort of modality structure, which is a semiring-like structure along the lines of McBride and, again, many others, where the algebraic operations of the modality are used to define the type system. For this general modality or modal language, we show a preservation theorem analogous to the typical type preservation of subject reduction, that serves as one of the main sources of evidence that the system we have set up is reasonably or correctly defined. We then look at some particular instances that are able to track erasure, and we show that once we compile programs in a way that removes things that have been marked as erased, we won't affect the result of evaluation. This is our main soundness theorem for erasure. And at the same time, we also show that we get canonicity for natural numbers, even in the presence of postulates, as mentioned. The setting that we've been doing this in, the language that's been formalized, is a dependently typed language with a single Russell-style universe, pi and sigma types, a natural number type, and an empty type. And for the sigma types, we make a distinction between weak sigma types, which allow a form of pattern matching on pairs, and strong sigma types with projections and eta equality. This language is parameterized over modality, which we consider to be this algebraic structure, a type M, whose elements we call grades, and three binary operations, addition, multiplication, and meet, and two special grades, 0 and 1, where addition and multiplication forms a semiring with the 0 and 1 as the 0 and unit of the semiring, and the meet operator should form a semilattice with addition, multiplication, distributing over meet. The lattice structure induces the standard sort of partial order relation, as shown here. The distributivity requirement essentially ensures that addition and multiplication become monotone operations with respect to this partial order. These grades are used to annotate the terms in certain places. For instance, the lambda abstractions and applications here, these P's are grades. Here are some examples of possible modalities that one could be interested in using. We have primarily been looking at erasure on the left, where we have two elements, 0 and omega, with 0 representing things that are erased, and omega representing things that can be used any number of times. And here omega is the unit of the semiring. We can also get either affine or linear types by including a 1, which naturally is the 1 of the semiring, getting different interpretations depending on the lattice structure and the partial order. As we'll see, this partial order serves as a sort of compatibility condition between grades. So in the affine types case, the 1 and 0 are comparable. 0 is greater than 1. So this will essentially mean that things marked with the 1 should be able to be used 1 over 0 times. Whereas for linear types, for the linear types instant, 0 and 1 are incomparable. So they are sort of incompatible with each other. In any case, no matter which instance we choose to use, we need some way of checking that the grades that we write on our programs are correct. For erasure, for instance, this would mean that anything that be marked with a 0 is something that's actually safe to remove, something that doesn't contribute to evaluation. We'll be using this black triangle as a sort of typing relation, which we keep separate from the usual typing relation judgments. One could, and usually you would see that this is sort of combined with the usual typing judgments. Gamma here is grade context, which associates a grade with every free variable in T, similar to a typing context. And we can think of gamma as sort of representing how many times free variables, or given free variable, is allowed to be used, at least for some instances. With this interpretation in mind, defining this relation is fairly straightforward, and similar definitions have been made by many others before. One of the key ideas is that whenever a new variable gets introduced, for instance by lambda abstraction, we need to somehow associate a grade with this new variable. So in any such case, we want the term that introduces the variable to be annotated with a grade that we can use for this. So for lambdas, the grade p here is used to extend the context when we check the body, meaning that this variable is allowed to be used p times in the body. Or alternatively, the function argument can be used p times in the function. Then when we reach the variables, we need to check that the variable is allowed to be used one time in the context. So the context that we're using is the one that assigns exactly grade 1 to that variable, with grade 1 representing a single use, and grade 0 for all other variables, representing no uses, since those variables don't occur. In the middle, I also show here the standard typing rule for lambdas. Lambdas, of course, have a pi type, and as you can see, one of the annotations on the pi type is required here to match the one on the lambda, giving it also the meaning of how many times the function argument is allowed to be used. The other annotation comes into play when we check the pi type itself in the usage relation. Since this is a dependent type, G is a type family, so it contains a new variable, which again, like the lambda, we need to associate with some grade. And this upper Q annotation is what we use for this purpose. So this represents how many times the function argument is used to form G, the type of the codomain of this function. In the head example before, the 0 annotation on the arrow is the one kind of corresponds to the P annotation here. You can also see that here when we have two subterms, F and G, we would typically check each of the subterms separately and then add the usage counts of both of them together using the addition operation of the modality, which is lifted pointwise to context. This is not always the case, though. Applications, notably, we first scale the usage context of the function argument by P, which is the annotation on the application. This again represents how many times the function argument is allowed to be used, and the reason for this scaling using the multiplication operation is that if we were to evaluate the application, we'd end up substituting a new P times essentially into the body of the function. Notably, when P is 0, we end up not counting any uses, since the argument is erased. This rule doesn't actually check that the grade is correct. We could just seemingly put 0 always and end up not counting any uses. This is instead checked by the usual typing judgment, where the pi type of the function needs to be annotated with corresponding grade. The eliminator of the empty type, which we call empty rec, from the initial example, uses the same scaling method. Gamma, the usage counts of the thing that we want to eliminate, gets scaled by P, which we can choose to be whatever we want. Again, since this is a consistent language, we'll never end up running this branch, so the idea is that scaling with anything giving us any usage counts should be safe to do. Most interestingly, when P is 0, we can consider this to be an erased argument and not count any uses. Unlike in the example, this term has a type argument A, which we use for type inference. We check that this type argument is correctly annotated under some context, delta in this case, but since the type argument doesn't actually have any computational meaning, we don't add the resources to the others. This one final term I want to discuss, since this is abstract syntax, it's not particularly readable. Project is how we do pattern matching on pairs. It corresponds to this let binding below, where we pattern match on T, and the variables x1 and x0 can be used in U, corresponding to the two components of the pair. And again, we have a type argument that we check separately. Here we scale the usage counts of the pair by R, representing how many times the components can be used in U. Again, R could be 0, meaning that we don't allow the components to be used, but we still allow the actual pattern matching on the pair. This is perhaps not obviously something that is fine to do. Pattern matching on something will typically have some computational meaning. In particular, when there are several constructors, it would choose which branch to take. But since this is a pair, there is only one constructor, so the idea behind allowing this is that matching on a pair doesn't actually reveal any more information about the pair. We also have kind of weakening or subsumption rule. This is how the partial order can be thought of as a compatibility measure, allowing us to essentially change the context as long as it's fine to do as decided by this partial order. The main kind of evidence, as I said, why we believe that this is a correct way of setting up the system is this preservation theorem, stating essentially that if T uses variables as specified by gamma and T reduces to U, then U also uses variables as specified by gamma. So variable uses are preserved by evaluating programs. We then look at some particular instances that can track erasure. Actually, all three instances I showed earlier can track erasure using the 0. In general, the instances should satisfy some additional properties, which I won't go into, but notably the erasure instance can be used. So what we'll be doing, or have been doing, is define a compiler that compiles our programs in a way that things that have been marked as erased gets removed. And then we show that doing this is safe in the sense that programs evaluate as before. So our compiler looks like this. We compile programs to a non-typed language without any grades, without any types, but with this special lightning bolt term that represents a crash or undefined value. So we compile any types to undefined, since there is no proper representation of the types. And otherwise, we generally follow and keep the structure of the term and compile each subterm recursively. For applications, we notably make a distinction on the grade. When it's 0, we remove the function argument and replace it with this undefined term. And similarly for project pattern matching on pairs, when the grade is 0, we remove the pair and replace it with a pair where both components are undefined. In both cases, the idea is that we have marked something as erased, so it should be something that doesn't contribute to evaluation, meaning that it should be safe to replace it with anything. We then use a logical relation, which again I won't go into, to show the following soundness property. If we have some program, T, of a natural number type, which may use free variables corresponding, for instance, to postulates, but these postulates should all be used only in erased positions. So when we check that T is correctly annotated, we do so in the 0 context, where we assign grade 0 to all these postulates. and gamma should be consistent. So any postulates that we use should be consistent with each other and with the base theory. And we either have no raised matches or gamma is the empty context. If all of these are satisfied, then we can show that there is some numeral n such that t reduces to n, and after compilation, the compiled program also reduces to the same numeral n, showing that this compiler really didn't affect the evaluation result. So why this no raised matches constraint? To see why, let's look at this example. Again, the abstract syntax isn't very readable, so I have a more readable, concrete syntax on the right. In this program, we try to pattern match on some free variable, z, and then return 0. But this doesn't actually reduce to anything. We get stuck trying to pattern match on this free variable. And so the first part of the conclusion here can't hold. We don't reduce to a numeral. But notably, this isn't actually a problem with the compiler. This only talks about the source language. And in fact, if we were to compile this program, we'd end up replacing the free variable with a concrete pair, allowing the compiled program to actually reduce to a numeral. It could be the case that the second part of the conclusion, the canonicity for compiled programs, do actually hold without or with the raised matches, but we'll leave proving that as future work. Finally, I also want to mention a few other things that we do in the paper. I mentioned that we have a distinction between weak and strong sigma types. The reason being that, well, one allows pattern matching and one allows projections. They have different use cases. And it turns out they also need to be handled differently when we check variable uses. We also extend the system with graded sigma types where we can keep track of how many times the first component of a pair is allowed to be used. And we also look at an example of a recursive type, particular natural numbers, and suggest a way of handling usage count for the eliminator in particular. Unfortunately, we found out just last week that the method we suggested isn't going to work for instance, linearity. So we need to, future work is needed in that area too. To wrap up, just summarize. We've been looking at the graded type theory that's parameterized by a semiring-like structure, following the works of many before us. Proven in particular soundness of erasure instances. All of this has been formalized in Agda, and it's our hope that others should be able to build on our formalization in the same way that we started our work by basing our formalization on previous one by others. Thank you.
Questions? Ohad?
Hello. Oh, can you hear me?
Yep.
Yeah. Great. Thanks for the nice work. So the nice thing about this is that it's so general you can interpret erasure as different things. And there's two different ways you can interpret erasure in this. You can either say nothing depends on the erased thing, or only erased things depend on the erased thing.
Right.
Which one do you capture with the syntax?
Only erased things are used by erased. Yeah. Erased things can use other erased stuff.
Okay, thanks.
Neil?
Hi. Thanks for a nice talk. When I was looking at your slides, one question that came up to me was, can dependent types depend on erased variables? So, like, if you had a head function which took an erased length and then a vector, could you allow that dependency to occur? or is it not allowed because it's a zero and you can't have free variables that?
So that is basically the point of this, that we can allow the type and the term to track, well, to use variables differently. So the type, if q is 0, then, well, yes. You should be able to. Can you show me the function?
Yeah. I wrote it because I thought it would be too hard. I'll just bring it up to you.
Thanks.
Yeah.
Right. Yeah, this should be fine. So in this case, then p would be 0 because the natural number is not used by the function, but q would be 1 since it's mentioned in the type once.
Okay. Thank you.
Okay, and the other side of the room. Yeah.
Hi, thanks for the talk. I have a question regarding propositional equality, because that's something that your slides didn't mention your language having.
No.
So I was thinking, if there was propositional equality and you also allow user-defined postulates, would that break canonicity? Because you could always define a bogus postulate like false equals true, and then you use that with equality to coerce something into something bad. Is that something?
I mean, if you postulate false equals true, then you wouldn't have a consistent postulate.
But
so
then you don't know, like, how do you know what's consistent when it's a user-defined postulate, right?
well, you would kind of need, if you want to use the postulate, you would kind of need to trust yourself that the postulates are consistent or prove that they are consistent somehow. As for the equality, we don't have equality. We've looked into adding equality a little bit. It seems not entirely straightforward, but it should be possible to do.
Okay, thank you.
Ian?
So I have a close enough. Or,
That's not possible. It's my case.
okay. Is it good?
Yes.
So I know that in ATKI system, there isn't a separate right triangle judgment. It's more like the usage tracking is baked into the typing judgment itself.
Yes.
Is there a specific reason why you sort of factor out the usage tracking?
Originally, because we started with the formalization that already had a typing relation, it was sort of easier to just add a separate one because you didn't have to change everything else in the formalization.
I see. And the second question is, earlier you said you treat strong existentials and weak existentials differently. But from my understanding, if you have a dependent elimination and you have a weak existential, you can sort of recover the projection operators, or is that not the case?
Yes, sort of. This thing, kind of, if you define the first projection using this, you would get some usage rule from this, which would be different from the one you would have for just defining the first projection as a kind of primitive thing. Basically, for some instances like linearity, you wouldn't be able to define the first projection using this in a way that satisfies the usage relation.
Okay, that makes sense. Thank you.
Okay, and last question.
So my question goes on a tangent a little bit. On the very last slide, you said that the formalization has 39,000 lines of code.
Yes.
And I was surprised by that. So I just wanted to hear your user's perspective. Is that an effort that you think is appropriate for what you achieved? And if not, what needs to be different about the world we live in so that, what makes it so big? If you think it's big, what makes it big and what could be different?
So, I'm not convinced that lines of code is a good way of measuring this. I think we might have had a different style than the original author, so we might have more lines per actual produced proof than what they had. But I don't know. I think that there are proofs that are very long without actually saying anything interesting because there are a bunch of necessary steps that you need to do to convince Agda that you're doing the correct thing, but that you would just skim over if you wrote a pen and paper proof. I don't know if this answers your
Well,
question.
could you imagine not having to do that, and how would that look like? Just from your personal perspective.
I don't know. One of my co-authors thinks at least that one should be able to write some tactic or meta program that could avoid having these long proofs, which would be very nice. I'm not really experienced enough with that part of Agda to say if that's possible.
Okay, thank you.
Thank you.